that's a control system. And such a system can be represented quite simply in the following way. So you have a kind of system which is a black box. You have some input to system like current or whatever, and the system delivers some output. But of course, you'd like to regulate the output depending upon the surrounding circumstances. So there's a controller which kind of feedback into input and lets you control what's happening in the whole system. So in version 14, you can study systems using desolve value. So you have the following notation. You have U of t, which is the input. Sys is a system which could either be a state space model or a transfer function model. And then the system responds in some way depending upon the input. So if the input is a Dirac delta function, it's an impulse response, and otherwise it might be some quite general output response. So I'll talk about all these things in the next example. So here is an example of a control system being solved with desolve value. So that's a transfer function model. It's like a Laplace transform. The S is what we call a Laplace variable. It's a very simple rational function in this case. And the behavior of this transfer function, which is basically like a mirror of the system in Laplace space, depends upon the poles of the transfer function. So here you see a complex plot of a transfer function. And notice that there are two shiny spots, the poles over here, and they both kind of lie to the left of the y-axis, and they're symmetrically placed about the x-axis. So you have a kind of negative real part to them and also imaginary part. So you'd think of these as being a combination of oscillatory and decaying behavior. And you can check the roots actually using the roots function like over here. So those are the real parts, negative, and the imaginary parts. Now, you can use desolve value in version 14 to find the impulse response. So that's the response of the system to a Dirac delta input, and that's the answer over here. But you could also say, I want to find the output response for, let's say, a sinusoidal input. You can do that over here, and you can say output response, and you get back the answer. And the question is, what is the relationship between these two, the impulse response and the output response? Well, the idea can be best understood using the new univariate unilateral convolve function in version 14. So what unilateral convolve does, it takes the input function and kind of it mixes it up with the impulse response and delivers the same result for the output response. So that is the unilateral convolve function. It's a very nice way of looking at the whole problem. And finally, over here, you have a plot that shows both the impulse response, the true response system, the blue graph over here, and the output response, the orange one that depends upon the input. And of course, you might have a discrete system. So those can be solved using either R-solve value or recurrence table. So that's one important new feature in version 14. And I now go on to the vector and contour integral functionality. So in version 13.3, we introduced three new functions: line integrate, surface integrate, and contour integrate for line, surface, and contour integrals in the complex plane. And in version 14, we have the corresponding functions for numerical, vector, and contour integration. And they are called n-line integrate, n-surface integrate, and n-contour integrate. So as an example, here is a classical surface called the Dupin cycloid. It was studied by James Clerk Maxwell and other people as well. And here's the beautiful plot of this surface. And you might ask, what is the volume enclosed by this surface? Well, to do that, you apply the Gauss divergence theorem. So basically what you say over here is, here's a vector field whose divergence is 1. And once you have such a vector field, then you can work out the surface integral of this vector field over the region, the Dupin cycloid in this case, using the new n-surface integrate function, because this is a very difficult symbolic computation, and you get back the answer for the volume using the Gauss divergence theorem. So the point over here is that we did have symbolic functions, but the new numerical functions will provide a very nice alternative to the symbolic methods. Okay, now for quite some time, we have been returning inactive or unevaluated sums from dsolve and asymptotic and other functions. And the question is, how do we extract useful information from these answers? So we have a wonderful new function called truncate sum in version 14, which makes it really easy for you to work with such results. So here is an infinite sum. It's unevaluated. I apply truncate sum to it and ask for the first 5 terms, and you get back just the first 5 terms of the infinite sum. And as a real application of this, here is the result from asymptotic for the full power series of sine x. You can see x goes from 0, is around 0 and has infinitely many terms. And you can say I want the first 8 terms of this power series, and it can do that for you quite easily. And once you've got that, then of course you can plot several truncations and get a beautiful plot like this one. So what truncate sum does is it cleans up the workflow for many calculus functions in our system. Okay, going on to numerical equation solving. So we have had nsolve in the system for a long, long time, but in version 14, there's a huge advance based on the notion of monodromy. This is a notion from classical complex analysis, and to understand the ideas, just think about finding the cube roots of unity, for example. So that's the equation z cube equal to 1. But think of it slightly more generally as the equation z cube equal to p, where p now goes around the unit circle. Now, because you got z cube equal to p, so roughly speaking, z is p to the power 1/3. So when p makes a complete round around the unit circle, you find the 3 different roots, the cube roots, because it goes at 1/3 the pace, and you can keep on doing that with different initial points and solve very, very large systems of equations numerically using this method. So this system method can be used for exams which have got many, many roots. And when I say many, I do mean a very large number. Now, of course, you've got a very large number of roots, then you need an option for it. So we have got the max roots option, which can be used to specify how many roots you want from the system. So for example, over here, I'm using nsolve to solve a system which has actually got 1 trillion roots, a very, very large number of roots, because 10,000, 10,000, 10,000, that's going to give 1 trillion roots. But I could say, I just want the first 5 roots over here, and it'll do that for you quite easily. So you might ask, what's the point of this? Where does all this come from? Well, this work was motivated by developments in engineering, and in fact, it's already been applied to robotics and other areas. But for us, it's one more general, powerful method for handling large systems of equations, both polynomial and transcendental. Okay, so in version 13.3, we introduced finite fields. That was a very nice feature, but in version 14, we have added several new features in this area. So for example, you can now specify a finite field using not just, let's say, finite field 17,3, but you could just say finite field 17 cube, and it'll quickly figure out for you what the finite field is all about. Or you can take an integer, like 21 in this case, and convert it to a finite field element. Now, we all know, and let's say we all students, we all tried to prove the so-called Fermat-Last theorem, which says that the equation x raised to n plus y raised to n equals z raised to n for n greater than 2 has no non-trivial integer solutions. And that's, of course, true for integers. But when you go to finite fields, like this one over here, the finite fields for 17 cube, then you can actually solve these Fermat equations, find points on the Fermat curve quite easily using version 14. So the point over here is that the finite field world is a world in which many things work, and it provides like a testing ground for many algebraic and number theoretical applications. But of course, the applications go well beyond pure mathematics, and things like cryptography use finite fields quite a lot. So the new version 14 documentation has nice examples for applying finite fields in the real world. Okay, so going on to linear algebra, we have new structured matrices. That's program that started in version 13.1, and version 14 is really a wrap-up release for this. We have 4 new structured matrices. We have symmetric matrix, which we all know, the Hermitian matrices, which are the complex cousins of symmetric matrices, orthogonal matrix, which is for rotations, etc., and its complex cousin, the unitary matrix. So these new matrices will be quite useful for many applications. Now, the point is we have an option called target structure, which lets you decide whether you would like to return these answers from other matrices. So for example, here I'm giving half a symmetric matrix, and I can apply symmetric matrix to it in version 14 and get the full symmetric matrix back. Here's the matrix in its matrix form. You can then ask the question, what are you good for to the matrix? It will tell you what the algorithms it's good for. So these matrices are very kind of self-aware. They know a lot about themselves, so they're really wonderful in practice. And of course, symmetric matrices have been studied for a long time, but even now, people need very high performance algorithms. They keep on coming up. So here is the calculation of the pseudo inverse for a very large symmetric matrix. And you can see over here that the calculation finishes up quite quickly. And as another example, here is a rotation matrix for rotation through angle theta and around z-axis. And you can say target structure goes to orthogonal, and you'll get back an orthogonal matrix. But if you'd rather like to have the old version 13.3 form, then you can say matrix form, and then you'll get back the original matrix as you'd like to see it. So it's not just other matrices, but also matrix decompositions, such as the Schur decomposition, etc., which will start returning these new structured matrices if you use the target structure option. So linear algebra is an important area. We are well aware of its importance in machine learning, other areas. We are trying to keep ourselves as close to the latest technologies as possible. And so another improvement for linear algebra is interval matrices. So we have been adding interval computation for special functions for quite some time. And in version 14, we now added for 12 basic matrix functions, including inverse, linear solve, det, and eigensystem. So an example here is a centered interval matrix. It's got interval entries. So in other words, your input is known only up to a certain error, in this case, something like 10 to the minus 17. And you can compute the eigenvalues, and you get the kind of rough estimate for what the errors are in this case as well. And if you like the conventional kind of output for eigenvalues, you can just do normal and get back the standard result. But interval computation is something that's becoming more and more important, and we would like to extend our reach to other areas for interval computation. Okay, so as a final piece of the algorithmic improvements, we have a new bilateral hypergeometric function. So what is the bilateral hypergeometric series? Well, it's very similar to the standard hypergeometric series. It's got factorials, Pockhammers, what I like to call them over here. But the word bilateral simply means that you're going from negative infinity to positive infinity. So it goes in both directions, and the new function bilateral hypergeometric PFQ implements the series in version 14. And when we did this, we weren't quite clear what such a function would be good for, but we realize now that it's wonderful for evaluating doubly infinite sums which go on both the sides. So here is a doubly infinite sum which, for whatever reason, took around 45 seconds in version 13.3, and now it just takes 0.01 seconds at the most, because we internally converted to bilateral hypergeometric PFQ, and then there's some auto simplification. And the second example over here shows the definition of the bilateral PFQ function in a real example. So this is the last piece in the hypergeometric puzzle, at least for now. So around 30 or more years of development have led to what we have in the system today. And going now to documentation, so we have two large documentation systems in the Wolfram language, really. There's the Wolfram language documentation itself, which is large, and we have MathWorld, a wonderful resource. And the question is, could we try and understand how well they each cover the other's territory, so to speak? So we did a survey of the coverage of our functions on MathWorld, and we figured out that there were lots of links which could be added from our documentation MathWorld to make it easy for users to learn about new functions and their information. So we have added around 150 new links to our reference pages for version 14. So for example, the page for Jacobi SN now will link to the MathWorld page for Jacobi elliptic functions. And we like to do more over there, update MathWorld as well. But I think this development makes clear that, we really do want people to use our system, not just any part of it, but all of it for learning in different ways. And talking about learning, I should mention the online courses. So we've been doing these for quite some time, but 2023 was a wonderful year, a very exceptional year. We had 5 new interactive WolframU courses in 2023: probability, statistics, multiple calculus, discrete mathematics, and the last course for the year, finite mathematics, was released at the end of the year. This is what is studied by the business majors and other majors in this country, in the US. But I think compared to any other course, this is a course that we valued a lot by students who struggle with mathematics, who need to get more intuition to understand what's really happening. But I hope that the finite mathematics course, which is one of our best taught courses, will get the audience that it deserves. And going forward, we are now working on a course on electric circuits, which should be a fun course. Just enjoy yourself studying electric circuits with us. That should happen sometime in spring 2024. So this is the whole set of features we have for 14 in a very short amount of time. But I should, at this point, thank everyone who's been involved in this effort, the developers in the team, other team in the company, and of course, all of you users who keep us motivated to develop more and more stuff. So I'd like to end with a sincere thank you to everyone who's here today, and to everyone at Wolfram for all the support, encouragement that we get to continue doing what we're doing. And we do hope to continue this for many more years to come. So on that note, I'll conclude my talk. It's been a great pleasure to speak with you today, and I'll stop over here. So thank you very much, and I'll stop over here.
Hello, my name is Adam Strzeboński, and in this part of the new in version 14 series, I will talk about finite fields and their applications. So let me first give you an overview of the new finite field functionality. First, representation of the finite fields. We have functions finite field and finite field element. Next, for finite field operations, we have arithmetic operations that work with finite field elements. We have finite field elements: trace, norm, primitive q. Minimal polynomial works with finite field elements, and multiplicative order works with finite field elements. Then we have finite field mappings, which is Frobenius automorphism and finite field embedding. We have conversion utilities to finite field from finite field index from finite field index. We have operations on polynomials over finite field. So polynomial GCD, LCM, and extended GCD work over finite fields. Factorization functions work over finite fields. Expand together, cancel will work over finite fields. Polynomial quotient, remainder, resultant, and discriminants. These are all the polynomial functions that work for polynomials with finite field elements, element coefficients. Then we have linear algebra functions that work over finite fields, dot, matrix power, determinant, characteristic polynomial, inverse, linear solve, LU decomposition, row reduce, null space, and matrix rank. And finally, we can solve equations over finite fields, so standard equation solving functions, solve, find instance, reduce, and resolve all work over finite fields. So let's talk about finite field representation. A finite field is represented by finite field Pf and rep, where P is a prime number, F is a polynomial function irreducible over Zp, and rep is either polynomial or exponential, so it's a representation type for the finite field. P is called the characteristic of the field, F is called the field irreducible of the field, and the degree d of f is called the extension degree of the field over Zp. So the finite field ff has p to the power d elements indexed by integers between 0 and p to the power d minus 1. So this constructs a finite field with 7 to the power 5 elements. So here is the representation of a finite field. We can look at details, see field irreducible, and by default, we get a field with polynomial representation. So this gives the element of the field with index 1, 2, 3, 4, 5. And now field elements are represented by finite field element objects. So this is a display form of a finite field element object. So the head of it is finite field element, and this is an atomic object. So we can look at it like this, open the details section, but we cannot take parts of it. It's an atomic element. Elements of finite field can be expressed as polynomial of degree at most d minus 1 in the field generator, where the field generator is a root of the field irreducible. So this specifies a field element through a coefficient list of a polynomial in data in the field generator. And we can extract information about field and field elements. So for instance, this gives us information about the field characteristic, field irreducible, and field size. And this gives an element, information about a field element. So it extracts the index, the coefficients in the field generator, and the finite field. And alternatively, we can get the index of a field element by just saying B of index. So now, first, let's talk in more detail about polynomial representation. So the default polynomial representation, the index of the field elements is equal to the evaluation of the polynomial representation in terms of theta at the prime number p, at the field characteristic. So for instance, this constructs the element with specified coefficients. And well, let us compute the index as the value of this polynomial with these coefficients at powers of the characteristic. And indeed, we get the index, the same index as we can see in this field element. And this finds coefficients from the index. So it's reverse of the integers digits. Now, an alternative representation is a polynomial representation. So we choose the field reducible to be a primitive polynomial, and hence each non-zero element of the field is a power of the field generator. So the index of the field element, which is a power, kth power of the field generator, is k plus 1. And the index of the field 0 is 0. So this is the indexing in this representation, and the exponential representation provides a somewhat faster finite field element arithmetic than the polynomial representation at the cost of precomputation necessary when the field is created. So we have to pre-compute so-called Zec logarithms in the field, and the pre-computed table of Zec logarithms has size proportional to the number of field elements. Hence, the exponential representation can be used only for relatively small fields. So the field has to have less than 1 billion elements for us to be able to compute the exponential representation. So for instance, this constructs a finite field with 19 to the power 3 elements. In the exponential representation, the output form looks the same as before, but we can see here the representation is exponential. So now let's compute the field generator using the coefficient specification. So fields of 0, 1 in each representation will give the field generator. And the index of the field generator is 2 because it has exponent 1 and we add 1. And here's the element theta, so the generator to the power 1 to 3. And well, it will have the index 1 to 4, the exponent plus 1. So now let's add 2 powers of theta, 5th power and 7th power. Now we see that this is 2873rd power of theta. That's computing this number. That's what we need the Zec logarithm table for. Now, which element can still be represented as a polynomial in theta of degree at most d? So we can find the coefficient of an element in the exponential representation. We can still find its polynomial coefficients in theta, and we can verify the correctness of the coefficients. That's indeed the polynomial evaluates to a. Okay, now let's talk about operations on the field elements. So we can do arithmetic operations. For instance, here are two elements of a finite field. We can evaluate rational functions in those elements. So we can add integers and rational numbers to field elements. They will be automatically treated as field elements in the prime field that is contained in every finite field. So for instance, this adds 3 to A, and this computes some finite field element properties. So this is the norm of A, this is a minimal polynomial of A, and this is a multiplicative order of the element B. So B to the power 16,806 gives 1. Okay, now let's talk about finite field mappings. The Frobenius automorphism is given by pth power assigning to a field element a pth power of the field element. In a finite field with characteristic P, this is an automorphism. And actually, all automorphisms of the finite fields are functional powers of this automorphism, which is called Frobenius automorphism. And we have the different automorphism. So, of course, automorphism preserve field operation, which we can check on our 2 elements that we defined before. Now this finds all conjugates of a field element, so the values of Frobenius powers of Frobenius automorphism at these elements. So conjugates are roots of the same minimal polynomial as our original element. So we can check that all the conjugates have the same minimal polynomial as A. And indeed, they do. So now let's construct a larger field. So we construct a field with 7 to the 15th power elements. And this field will contain fields that are isomorphic to our original field F, but there is no unique isomorphism, so we cannot just add an element of FF to the element of GG. We will get error message saying we cannot add two elements from different fields. So we know that FF is isomorphic to a subfield of G, but we have to find an explicit isomorphism. So this will find the isomorphism, an embedding of FF in GG. And now we can map the element through the embedding. And now we can add the result of embedding of A to an element of G. And of course, embeddings preserve field operations. Now let's talk about polynomials over finite fields. So for instance, factor can factor polynomials over a finite field. So we can start with a polynomial with integer coefficients. This will embed the coefficients in the finite field and do the factorization over the field. So this polynomial factors into linear factors, one with one double factor over F. Now we can compute with polynomials whose coefficients belong to FF. So this gives a polynomial quotient and remainder of two polynomials with finite field coefficients. And we can check that indeed these are the quotient and remainder. So we get 0 here. And expand works over finite fields. This computes a discriminant of a polynomial with finite field coefficients. And this cancels a rational function over finite field. Since we divided x minus a by minimal polynomial of A, well, it had to be cancelable. It's one of the factors of the minimal polynomials. Okay, now let's talk about converting coefficients. So we have functions to finite field and from finite fields that can be used for converting between polynomials with finite field coefficients and polynomials with integer coefficients. So starting with polynomial with integer coefficients, we can convert it to polynomial with finite field coefficients. Of course, all the coefficients will be in the prime field of this finite field. And now we can factor the result over the finite field. Now we can convert finite field element coefficients to polynomials in T, where T represents the field generator. See, they are not all in the prime field, so we cannot convert them to integers. We have to have some way of representing the generator of the field. And here is the representation. So we get factors linear in X and which are with coefficients that are polynomials in T. Here let's collect coefficients at the power of X. And now we have reverse operation. We can convert the result to the finite field where T will be taken to represent the field generator. And we got the original polynomial back. Okay, now let's talk about linear algebra functions that work over finite fields. So let's generate a random matrix of finite field elements. So we generate randomly the matrix of indices, and we use function from finite field index, which will convert indices to field elements. And this way we generate random matrix of finite field elements. Now we can compute matrix power. Since the coefficients in the matrix will not grow because they are in the finite field, we can use really large exponent and compute the power. And let's compute the determinant of the matrix, the inverse of the matrix, and this just checks that it is indeed the inverse. And finally, solving equations over finite fields. So let's solve a univariate equation over finite field. So here we had finite field coefficients. That's why we get solutions over a finite field. Here we start with integer coefficients, but we say that the domain is the finite field, and we get the solutions. And this solves system of equations over a finite field, and this finds an instance of an equation and an equation over finite fields. See, this would not have solutions over complex numbers, but over finite fields it does. Okay, so applications over finite fields. Finite fields are used in algebraic computation, error correcting codes, cryptography, combinatorics, algebraic geometry, number theory, and finite geometry. So for the first application, let us construct Diffie-Hellman public key crypto system that allows you to send encrypted messages in 128-bit parts. So first, let's find a prime field with 128-bit characteristic. Now we find a primitive element of the prime field. So now the first user who will send the message chooses a private key, which is a number between 2 and p minus 2. So let's choose it randomly. And now the public key will consist of the field itself, the primitive element of the field, g, and the power, the g raised to the power a. Now the second user chooses, again, a number b between 2 and p minus 2. Choose it randomly. And to send a message, let's randomly generate a message. The user sends m times g1 to the power b and sends g2, which is equal g to the power b. So let's compute m1, m times g1 to the power b, and g2 to the power b. So the first user can recover m by computing e divided by g2 to the power a. And let's see that the index of this element indeed is the message. And security of this system relies on the fact that to decode the message, you need to know what a is, and computing a from g to the power a and g is difficult. It's so-called discrete logarithm problem, and it's hard to solve. That's why the system is secure. Okay, so for the second example, let's show how to generate Sidon sets. A finite set A1 through AN of integers is a Sidon set if all the sums of all pairs of elements of the set are distinct. So Sidon sets involving arbitrarily large integers are easy to construct. So finite set of powers of 2 is a Sidon set in the interval 1 to the power n-1. However, the size of the integers involved is exponential in the size of the Sidon sets. We have only n elements in the Sidon set, but their size is up to 2 to the power n-1. Now, using finite fields, we can construct Sidon sets with the size of integers involved that's only quadratic in the size of the Sidon set. So this will construct a Sidon set of q integers in the interval from 1 to q squared minus 1, assuming that q is a prime power. So we construct a finite field with q squared elements in the exponential representations, and this will generate a Sidon set. This is looking at for a while to understand why. So I will not discuss it here, but let's show that we can indeed construct a Sidon set using this code. So for instance, if we pick q equals 49, this gives Sidon set with 49 elements. So length SS should be here, not A. Now it's true. And we verified that all the sums of pairs of elements are different. So length sums will be equal to the length unions of sums. So they will be distinct, and their number will be q times q plus 1 by 2. And again, for some reasons, I have A here instead of SS. Now it will behave better, and indeed the verification works. And this was the last example. Thank you for listening.
Hello, I'm Aram Manaselian from Calculus Algebra team of Wolfram Research, and today, during the webinar new version 14, I will speak about connections between calculus and control. Here is the outline of my talk, but first I will give a brief introduction about control systems, their connections to calculus. Next, I will speak about system models and their implementations in Wolfram language. Next part of my talk will be about how we can solve some linear system models using symbolic calculus tools such as dissolve or dissolve value. Next part of my talk will be about one of the new features of version 14 about unilateral convolution and its possible applications in control systems. And finally, the last part of my talk will be about discrete time system models and their solution methods using symbolic calculus tools in Wolfram language. So let's start. Recently, control systems and control theory became more and more attractive, not only for engineers, but also for researchers from different areas such as physics, chemistry, biology, mathematics, etc. Here we can see a simple schematic picture of a control system. We have an input which goes to the system, and system generates some output response. Also, we have a controller which checks the output and makes changes in the input in order to control the actual output response from the system. And here, one of the most important elements is the system model, which takes into account the input and generates output. And for the case of dynamical systems, with system models are mostly governed by differential equations or systems of differential equations. Therefore, they are very closely related to calculus. System models are already implemented in Wolfram language. Currently, we have 4 types of system models, which are well known from control theory textbooks. These models are state space model, transfer function model, affine state space model, and nonlinear state space model. The first 2 are linear models, which can be governed by linear differential equations, and last two are nonlinear models, which can be governed by nonlinear differential equations. The nonlinear systems can be solved mainly using numerical methods, so we are beyond the scope of my today's talk, but is why I concentrate my attention only to first two system models. In order to understand what is the state space model, let's consider a simple dynamical system which can be governed by a very simple first order differential equation. In this equation, x of t is the dependent variable or so-called state function. U of t is the input function. And suppose we want to generate following output response from this system. Here A, B, C, and D are constants. In order to generate the state space model of our system, we can use state space model built-in function with following arguments: equation, state function, input function, response function, and independent variable or time. And as a result, we will get this state space model presented here. As you can see, the model doesn't contain any of state functions, input functions, response functions, etc. All of them are defined internally inside the system model. Alternatively, we can use more simplified version of state space model function with just A, B, C, and D, and we will get the same result here. Now, if we want to solve this state space model, we have to extract the equation from it, and then we can try to solve it using dissolve for a given value of input function. In this example, it's unit step function. And the solution of this differential equation will be the state response of our system. Now we can substitute this solution into the response function to get the actual output response of the system, which is presented here. In general cases, in state space models, the x and u can be vectors, and A, B, C, D can be matrices, which would respond to more complicated multiple input, multiple output systems. In the case of transfer function model, we are using a Laplace transform of the differential equation. Again, let's consider the same simple dynamical system, which can be governed by this equation. Now we can calculate the Laplace transform of this equation. As a result, we will get a non-differential equation presented here, where x of s is the Laplace transform of the state function, and u of s is the Laplace transform of the input function. We can solve this equation to find x of s, and then we can calculate x of s divided to u of s, and the obtained expression can be used as an argument for built-in transfer function model, which will generate the transfer function model of our system for us, which is presented here. As you can see here also, we don't have any state functions and input functions inside the model. All of them, again, are defined internally inside the system. And if we want to solve this system model, again, we have to extract the equations back from the system, solve it to generate output responses manually. But here I want to mention that in version 14, we have implemented support for linear system models in dissolve value. So now you can just simply insert the state space model or transfer function model inside dissolve value, and dissolve value will do all the job for us. It will solve the model and will return corresponding state responses or output responses for given input function. But here you can ask a question, why dissolve value and not dissolve? And in order to answer this question, we have to go a little bit deeper under the philosophy behind these two functions. Usually, dissolve returns all possible solutions of a differential equation as rule. For example, if you try to solve this differential equation using dissolve, you will get this type of expression. Y of x goes to a function, which is the general solution of the differential equation. In contrast to this, dissolve value returns only one solution of differential equation as an expression. So if you try to solve the same equation using dissolve value, you will get only the general solution without any rules. But this is not the main difference between dissolve and dissolve value. Dissolve has some strict rules which cannot be broken. For example, the first argument of dissolve always must be an equation, a differential equation, or a list of differential equations, together with initial and boundary conditions, which are also equations. The second argument of dissolve must be a dependent variable or the list of dependent variables in case of systems. And the third argument of dissolve must be the independent variable or list of independent variables. For the case of dissolve value, again, the first argument must be the equation, but the second argument can be almost any expression. For example, if you want to solve a system of two differential equations, and suppose you want to get only the solution for one of the dependent functions. For example, here we have a system of two differential equations and two dependent variables, y of x and z of x, and we want to get the solution only for y of x. If you try to do that using dissolve value, for dissolve will generate an error message and will fail. But we can easily do that using dissolve value, as it is presented here. And even more, we can ask dissolve value to solve a differential equation and return, for example, the square of the solution. And we can do it just putting y of x squared as a second argument of dissolve value. And this also will work. The second argument of dissolve value can be also a number. For example, we can ask dissolve value to solve a differential equation and return, for example, 1. Of course, this makes no sense, but it will work. And finally, the second argument of dissolve value can also be a string. For example, we can ask dissolve value to solve a differential equation, and instead of the solution, return, I know the solution of this OD, and this also will work. And this flexibility of dissolve value make it easier the implementation of new features or new models of equations which can be solved without breaking any strict rules for the case of dissolve. Now let's go back to our system models. As I already mentioned, in version 14, you can use dissolve value for solving linear system models, and here is the design how we can do it. If you want to solve a system model using dissolve value, you can just write dissolve value u of t goes to system comma resp comma t, where u of t is the input function, sys is the system model, which can be a transfer function model or a state space model, and resp is a string which can have two values, state response to get the state response of a system to the input u of t, or output response to get the output response of a system to the input u of t. And here are some examples. As an example one, let's try to calculate the output response and state response of the state space model for a sinusoidal input. So at first we have to construct the model using the state space model command. And then we can try to solve it using dissolve value. So if you write dissolve value sine t goes to the model, comma, output response, you will get the output response of the system to sinusoidal input. And if you write dissolve value sine t goes to the model, comma, state response, comma t, you will get the state response of the system model to sinusoidal input. And as a second example, let's try to calculate the output response of a transfer function model to sinusoidal input. In this case, I have inserted the transfer function model inside the dissolve value. So I just write dissolve value. The sine function goes to transfer function model, comma, output response, comma t, and this will give the output response of the model to this input function. As a third example, let's try to calculate the response of a state space model from non-zero initial conditions. In this case, I have a more complicated state space model, but I don't have input function, so I put 0 here. But instead, I have non-zero initial conditions defined in this part, and I want to get the output response. And here is the result. And as a fourth example, let's try to calculate the response for a multiple input, multiple output transfer function model. In this case, this is our model. And this model needs 2 input functions. So I defined 2 input functions here, which are going to the model. And I want to see the output response for this period of time. And this is the result. And here is the plot. We have also some special cases for which we have a little bit simplified design of the solve value. And these special cases correspond to most commonly used 3 input functions, which are the Dirac delta function, unit step function, and ramp function. And for these 3 functions, you can use this solve value with a simplified design, which is presented here. You can write this solve value system, comma, resp, comma, t, where this again can be a transfer function model or a state space model, but resp is a string which can have, in this case, 3 values: impulse response to get the output response of the system for Dirac delta input, step response to get output response for unit step input, and ramp response to get the output response from ramp function input. And here is an example to demonstrate this. Let's try to calculate the step response, impulse response, and ramp response for transfer function model. So this is the model. And if you want to get the step response, we can write this solve value, the model, comma, step response, comma, t, and this will be the result. And for the impulse response, we can write this solve value, model, impulse response, comma, t, and we will get the impulse response. And for ramp response, we have to write here just ramp response. And here is the plot of 3 responses. And I want to say that much more details and more examples about this new feature of version 14 can be found on the updated reference page of this solve value in version 14. And now let's consider a simple application example. Let's try to model the mechanical mass spring damper system. Here we have a mass M connected to a spring with spring constant K, and we have a damper system with damping parameter B. And this is the equation which can govern this system. Here x of t is the state function and f of t is the external input force. At first, we can generate the state space model of the system using the state space model command of this form. And here is the state space model. Now we can try to calculate the responses of the system to various input forces. For example, let's try to calculate the step response of the system to unit step function like force. So we will get this type of symbolic expression. Also, we can try to calculate the impulse response of the system to Dirac delta-like impulsive force. In this case, we will get this type of expression. Or alternatively, we can calculate the response of the system to, for example, sinusoidal input. We will get another expression presented here. And finally, we can plot all 3 responses together for given values of parameters of the system. And here is the plot. Here, blue curve responds to unit step-like function. Orange line corresponds to Dirac delta function, and green line corresponds to sinusoidal force. The next part of my talk will be about unilateral convolution and its possible application in solving system models. The unilateral convolution has been implemented in Wolfram Language version 14. New system function unilateral convolve can be used for calculation of the unilateral convolution between two functions f and g. The concept of unilateral convolution arises naturally when examining causal systems. The output of such systems at any time depends only on the values of the input at the present time and in the past. The unilateral convolution between two functions f and g is given by following integral expression. The following picture demonstrates the unilateral convolution of exponential and unit box functions. First row demonstrates the two functions at different times. Second row demonstrates the product of two functions at different times. And finally, the third row demonstrates the unilateral convolution between two functions. More details about the unilateral convolution and unilateral convolve function can be found in corresponding ref page in version 14. But here I decided to speak about this new function because it has an interesting application in control systems. To demonstrate which, let's consider the following example. Let's try to calculate the output response of a transfer function model from a sinusoidal input. So this is the model. But at first, let's try to calculate the impulse response of the model from Dirac delta input. So this will be the impulse response of the system. Now we can calculate the unilateral convolution between impulse response and sine function. You can do that using following command. So this is the unilateral convolution between impulse response and sine function. The following animation demonstrates the convolution of impulse response and sine function. Again, here you can see two functions together. Second plot is the product of impulse response and sine function. And third plot is the unilateral convolution. And here we can show that the unilateral convolution between impulse response and sine function will be the output response of our system to sinusoidal input function. To verify that, let's also calculate the response of the system from the sinusoidal input using the solve value. This is the output response from sinusoidal input, and we can compare this with unilateral convolution result to verify that they are identical. This means that if you know the impulse response of some system, you can calculate its response to any other function using unilateral convolution without actually solving the system. And this technique is the analog of Green's function technique. In fact, the impulse response of the system can be considered as the Green function, which can be used for calculation of the responses for any other functions using unilateral convolution. And finally, the last part of my talk will be about discrete time system models. It is not possible to solve discrete time system models using the solve value because at first, the solve value does not support discrete variables. And second, the discrete time system models are governed by recurrence equations and not differential equations. That is why instead we can use R-solve value or recurrence table functions. And in version 14, we already implemented support for linear system models, also for R-solve value and recurrence table functions. So if we want to solve discrete system model using RSOL value, we can use following design, which is similar to DSOL value. We can use RSOL value, input function goes to the system, comma, response, comma t, where system again can be discrete time transfer function model or state space model, and response can be state response or output response. And here are a few examples. Let's try to calculate the output response and state response of discrete time state space model. We can construct the model using the state space model command together with sampling period option for discretization. And now we have a discrete time system model, and we can solve it using RSOL value, for example, for sinusoidal input, and this will be the state response, and this one is the output response. And as a next example, let's try to calculate the output response of a transfer function model. Again, we can construct the model using transfer function model command together with sampling period for discretization, and we can solve it using the RSOL value function. And in the cases when we want to solve discrete time system models for given interval of time, we can use recurrence table function. And design is again very similar to the case of RSOL value or DSOL value. We have input function goes to system, comma response, and comma time. And again, response can be state response or output response. And here is an example. And in this case, the output of recurrence table function will be a list of numbers. So we can use list plots for plotting. And this is the state response of a discrete state space function. And here is the output response. So this is all I plan to say during this webinar talk. Thank you for your attention.
I think it's been a good set of talks in the sense that I feel very satisfied that we've got kind of a lot of depth in them. There haven't been too many questions, so please feel free to type questions. I always admire people who ask questions, and what you ask us now becomes the basis for our, for our future plans. So what you saw today has been requested by people for quite some time. Finite fields have been tried forever. So from my talk itself, I think the one thing I'd like to emphasize is the NSOL improvements, which actually came out of a real PhD thesis from nearby Indiana at Notre Dame University. So one of our young student ambassadors came up to us and said, I've got this nice improvement for NSOL. I can solve systems with millions of roots. And it was hard to believe that, but it was a lot of work to get it done. Okay, but I'm quite happy it got done in the end. And apart from that, there's going to be some question about the bilateral PFQ, I'm sure, in your minds. So this is the very end of our PFQ developments, and the one person who has done a lot of work in that area in the 20th century was Lucy Carter at Cambridge. So she was a lady mathematician, and I told myself, okay, she must have worked on this topic for all her life. It turns out that for the second part of her life, she worked on operating systems. So who knows? Who knew that people do that? I think the finite field stuff is very deep, very applicable. For a long time, I've worried about how to do it myself for all kinds of things, and now we have a truly world-class implementation thanks to Adam. And the talk by Aram, I think if you should learn anything from it, is that we have DSOL value. Please use it. A lot of times people try something with us and they really want not DSOL but DSOL value. So I do see a couple of questions coming up, and I'll try and talk about that in just a minute. But meanwhile, maybe I should just invite Adam and Aram to add anything that they want to the whole thing. Adam, anything from you? Any kind of quick comments you'd like to make about anything that is on your mind today?
Not really, not at the time.
Okay, Adam is a very and he's very, very efficient, and he is already deep into our next release, but I shouldn't tell you too much about that right now. But I think that finite field stuff is really, really polished and nice with the applications and all the cryptography stuff. Aram, anything from you that you'd like to share in terms of your experience with the control systems project?
Yeah, I just want to add that, of course, dissolve and dissolve value are quite old systems in Mathematica, and we're always trying to improve them, to add new solution methods, new equations which can be solved. But in the last few releases, we are trying to go slightly different way. We are trying to add some new functionality and some new connections with other areas into dissolve or dissolve value. For example, in the last release, we have implemented fractional differential equations, and in this release, we tried to add some control systems functionality inside dissolve value.
Very good. So I think that we actually have come a long way with dissolve value. And thank you, Aram and Adam. So I'm quickly going to take up a question from Enrique about the complex analysis course. Well, believe it or not, we are almost into the recording stage for that course, and it'll be published, available to you sometime in late in the year, probably in fall. So the plan is in spring we'll do the circuits course. The complex analysis course is written in sense we actually have a textbook of complex analysis which starts with complex numbers, talks about analytic functions, goes on to Cauchy's theorem. I mean, I know these may not be just big words for most of you, but that course actually is making excellent progress. And internally, just by the way, Cassidy asked me just the same question, what's happening? And we have a very scholarly author for the textbook and presenter, Marco, who's actually trying to make this a combination of classical textbooks like Alfred's and Churchill and Brown, and very modern stuff from Mathematica, like complex plot and things like our contour integrate, residue sum, etc. So this should be an excellent course. It's going to be a bit more advanced than the average course we had before, but thank you, Enrique, for asking that. Yes, the course is very much under development and it should be available to you very, very soon, sometime in the year.